Hello, and welcome to episode 4 of my Getting Started with C course. In this episode, we will be discussing arrays. So far, we have looked at this simple program in almost all of the episodes, and we have been slowly picking apart different elements of it to try and understand what this means better. So far, we've spent a lot of time focusing on these main parts of the program, because there's the most complexity in these areas. After the last episode, we should have a decent understanding of what most of this means. For example, we understand that these are data types, and that these are the names of those variables that we've declared. And as a whole, we understand that this is a way we can bring in arguments from the command line when we run our program. But there's one key thing here that we haven't really explained yet, which is these square brackets. What are they doing there, and what does it mean? Well, this is the declaration of an array. So let's start with the basics and work our way up. First of all, what is an array? Well, at its simplest form, an array is just a list of values, a way of chaining multiple values together in a list, like you'd keep a shopping list or other notes. In some programming languages, you might see them declared like this. For example, this is how you would declare a list in Python. And as you can see, we can just mix and match data types and put them in a list. Now, this is not how C works, and so I'm going to make an important distinction. Arrays are not the same thing as a list. A list is generally a fairly high level object where you can store a bunch of random information. Arrays are homogeneous. You could only store the same data type in them. Let's look at a declaration of an array in C. Here, we have declared an array that stores integers, so it's of type integer, and it has the size of 3. And then on the right side, you can see the values that we're storing in that array. Now, this will all make a bit more sense later on, but one thing I want to highlight is that we can only store integers in this integer array. We cannot mix and match data types. Okay, so this is kind of where most tutorials would finish their explanation of arrays. We'd probably jump into doing some examples and just highlight some simple ideas about what goes wrong when using arrays. However, I want to go a bit further than that, because I think there's much to be gained from having a deeper understanding of what the computer's really doing when we're talking about arrays. So, if you can bear with me, I'm going to go into a much more fundamental detail about what's happening inside our computer when we do something like this. If you remember a few episodes ago, we talked about variables. And in that episode, we described variables as a kind of box that we can put data in and give a label. And we're going to extend this analogy a bit further. If we think of a variable as a box or a place where we can store objects, then it might stand to reason that if we have a lot more objects, we might need more boxes to store things. And this is where arrays will come in. But first we need to define what we really mean by box in this analogy. In modern computing architecture, the smallest amount of information that can be stored in memory is called a byte, which is an 8-digit binary number. Okay, if you're not super comfortable with binary, it's not the end of the world. Just understand that it's a different way of writing numbers, and it's a way that computers understand numbers natively. So when we're talking about the boxes in this case, I'm referring to bytes, or the smallest amount of information our computer can actually store. For example, 1 byte can be used to encode some character information. We've already seen the char or character type in our previous episodes, and this is just a data type in C that allows us to store a single character. Well, it turns out that a single character is exactly 1 byte of information, and we can encode most of the common Western alphabet using single bytes. So, what happens if we need to store more than 1 byte? Well, in our first example here, you can see that we're storing a single letter, so it stands to reason that it might only require a single box to store that much information. However, in the second example here, you can see that we're trying to store a string of information, which is 4 characters total. And so using our analogy, it also stands to reason that we might need to store 4 boxes worth of data here. We can put the letter A in one box for the 1 letter variable, but for the lots of letter variables, each letter is going to need its own box, because each letter takes up 1 whole byte in memory. Using this example, it's easy to understand that storing more information just physically takes up more space in your computer's memory, and this is true. But there's one thing we need to clear up. If we just have boxes with bunches of values everywhere, how do we keep track of which order we're supposed to read them in? How do we not get them messed up, and how do we know which ones belong to the second string and which ones belong to just being their own data? Well, we need to extend our analogy a little bit. If boxes are bytes, then we can think of memory as a whole as a kind of warehouse or data center which contains a whole bunch of boxes. And extending this analogy once more, we can think of the shelves in the warehouse as arrays, ways to store our box in an ordered fashion so that we know where to find them later. Let's go back to this example string of haha. Remember that because we have 4 characters, we need 4 boxes. 1 letter goes in each box. Now let's imagine that we have a shelf with those 4 boxes on it. We can then read the shelf from left to right in order to recover our information. As long as we store the letters in the same order we wrote them, then we can easily read back this information. Now, this seems a little bit trivial at this point because it's somewhat obvious, but we're going to keep extending this, so just bear with me. Now let's say we've got several strings stored in memory. How do we know which one to refer to when we're trying to retrieve a value? Now keep in mind, everything we're talking about now is very low level and not something that you as a programmer have to consider, but rather an explanation of how the machine finds information that we store. Okay, well as you can see, say we have 3 strings. Here we've got haha, nope, and help all encoded as arrays, all sitting on their own shelves. If we number the shelves, top to bottom, from 1 to 3, and then number each box position on the shelf from 0 to 3, starting from the left and moving across, we now have a sort of way of referring to where a certain character or piece of data is stored. If you've ever played battleships or done anything with grids, you'd be familiar with this concept. For example, we could say that we need to find the value stored at, say, 1 and 0, and you can see that that's the one at the top left, or the H value. And we could say we needed to find 2, 3, which is the E, which is the middle row on the right. So 2 being shelf 2 and 3 being position or index 3 on that shelf. And we can extend this further. Remembering that binary is just a way of representing human readable numbers in a machine format, we can translate these numbers to binary codes. Okay, the encoding system still works the same way here, but it's just a little bit more verbose. For example, the H at the top left becomes 0001, 0000. Okay, so if we take that position, for example, and we combine those two indexes, so we have the shelf number, and we take those 4 bits of information, and we take the index number, which was 0. Remember, these are just human numbers translated into binary. We now have a single number that represents that box's information in memory. And we can go ahead and do this for all the other numbers. Okay, this is starting to get a bit abstract, so to make it less confusing, I'm going to replace our human readable numbers here. Okay, so what do we have here? Well, now every single box with its own information has a unique memory address. That's what we call these little numbers. Let me grab out the laser pointer here. All right, so when we talk about a memory address, we're referring to these numbers. Now, the red is how a machine would see it, and the blue is simply here so that it's easier for me to explain because obviously we don't talk in binary, we're used to base 10. Okay, so when we want to retrieve the letter or the value that's stored in this box, all we have to do is know that we need to read from position 16 in memory. And for example, to get the A, we would need to read from position 17. And what's the benefit in doing this? Well, let's consider this example again. When we declare an array, or when we declare a string of characters, say in this case haha, what actually happens is that our computer, first of all, creates some space. It creates a shelf to store that information, right? And in this case, it needs to create 4 bytes. So it creates a shelf that has 4 boxes on it. And it then simply places them on the shelf in an order so that their addresses increase as we go along. When we do this, we don't actually have to store this information anymore because haha is now stored in memory. So this value here of text does not actually have to contain all of this information. Instead, all we need to do to be able to retrieve this information at a later point is store the address of the first value in this array. Again, it's a bit abstract, so just bear with me. We're going to bring it all back together at the end. Okay. That's what these asterisks mean. If you've seen these asterisks before, or these little stars, for example, this is sometimes referred to as a char star, what that actually means is store a pointer or store a memory address that points to the start of this string. And that's what really happens here. In this example, our computer will allocate 4 bytes to store these 4 characters, and then it will remember that those 4 characters start at this shelf position, or 16. And then from there, we can always find the rest of them by just increasing our number. It's important to realize that a star type is not the same as its underlying data type. The one on the right is a fundamental data type that actually means we are storing this kind of information. When you see something with a star, it means we are storing an address to where we can find that information. It's a little bit of an annoying distinction, but it's one that we make nonetheless. And here, yeah, once again, memory address, single character. Okay, and we're going to talk about pointers again in another episode, so don't get super weighed down. Just stick with me, I know it's a lot to take in. Okay, now let's break it down even further. Let's look at what happens in a really specific example. Okay, so here, what we're trying to do is create a numbers array, or an array of integers specifically, that's our data type, that contains 5 values. We can then assign values into the array by using these bracket notations, where we basically say which index we want to set and what we want to set the value to. Note that we start counting from 0 instead of 1 here. So despite the fact that our last index is index number 4, there is still 5 values being assigned. 1, 2, 3, 4, and 5. But why do we start counting from 0? Well, that's a common question, and I don't think it's often explained very well, so I'm going to try my best to give it a go. But it's important to understand here that when we're declaring an array, this number simply represents how much information we intend to store, in this case, 5 integers. But when we're assigning an array, we can just check each individual index, so the 0th position in the array, the 1st position in the array, all the way down to the n-1th position in the array. It's just important to realize that we always start counting from 0, so our last number will always be 1 less than the total length of the array. And we're going to explain why this is. So, starting from just looking at this declaration, when the computer sees this instruction, it says, create an array called numbers which stores 5 integers. It first goes and allocates enough room in memory to store 5 integers. Remember when we talked about shelves? Well, it stores 5 boxes, each containing an integer, and it puts them all on a shelf together. Okay, that's our array. It's an ordered set of boxes, each one of them can contain an integer. So when we declare this, and this is why we have to tell our computer how much information we intend to store, it needs to know how much boxes and how much space to create on a shelf. So we declare it, and then it allocates space on a shelf for us. Then we go ahead and we attempt to set the first number. And this here is the magic in counting from 0 in arrays. If we remember that when we declare an array, what we actually get is a pointer, okay? So we remember the memory address of the first element of that shelf. And again, the blue numbers here are just the human readable versions of these addresses, okay? So we declare this array, it allocates shelf space, but then what also happens is we store the first memory address of that array. So in this case, the numbers variable here gets set to the memory address of the first location on that shelf, which in this case is 8. That means that when we want to assign a number to the first position, we can simply get the memory address, add 0 to it, and then write our value to that position. So, looking at it here, if we take the memory address, add 0, then we can write 7 to it, and now we have set our first value as 7 in the array. Extending this a bit further, if we want to assign our next point in the array, we can simply take the original memory address, which was 8, and we can add 1 to it, which gives you 9, and that gives us the next position in memory in which to write our value. Okay, so now our index says 1, and that basically represents, take our original memory address, add 1 to it, and write this value into that position in memory. And we can expand this for all the variables we have to set. Okay, so right down to the end where we take our original memory address, we add 4 to it, and 8 plus 4 is 12, and now our computer knows where to write that information. Now, the reason why we do this is it's just really fast. The computer doesn't have to keep track of what order to put things in or remember where it stored stuff, because it only has to remember where it stored the first thing. It only has to remember the position of this first box, And because we've set up our shelves in a nice clean order, it means that it can always find the next index simply by adding 1. And this is a really fast operation. But this is why we have to count from 0. Because if we started counting from 1, we would miss this first address. Because remember, we're adding this index to the memory address. So this is our 0th position. Adding 1 to this address brings you to 9, and that would be the second element in our array. Now, that was a lot to take in, and it's not always obvious of how to apply this information once we've seen it in a tutorial. So now we're going to quickly jump over the editor and just code this brief example ourselves to see what happens. Okay, so we're back in our editor. I've got the folder opened up that we've been working on. This is obviously our main program. This is the thing we developed in one of the episodes, I'm pretty sure. Anyways, what we're going to do, as usual, we're just going to create a new C file. And you can see my folder's starting to get a bit cluttered. Don't worry if you don't have all the same files as me. It doesn't really matter. You only have to worry about the one that we're working on currently. I'm going to call this array.c because I think that's a good name. All right. So first thing we're going to do is start out by declaring our standard main loop, okay, which remember is int main, and we can take our arguments in here. However, if you know that your program doesn't actually need to take arguments from the command line, you can simply type void. So normally we've been used to seeing this, okay? And this is really useful if you want to take in arguments off of the command line. However, we don't always want to do that. So instead, we're simply doing this. Okay, so putting void in here, avoids just says, it just tells the compiler, hey, we don't need to take any arguments when this program is called. We don't need any extra information. All right. And it's a bit of a shorthand way if you know that that's the case. Okay, so this is setting up our main function as usual, and I'm going to make the text a bit bigger because I think it might be a bit small. And that's pretty good. All right, the next thing to do is returning 0 at the bottom of it. This just says that our program has exited correctly. So if we hit this point, it tells the operating system that, hey, everything went well. You don't need to worry about checking for errors. All right. Next, we're going to make an array. So we're going to make an array of numbers at first. So let's do an array of doubles. Remember that double is a type for decimals or decimal information. To declare an array, we simply have to say the data type of the array, the name of the array, and then in the square brackets, how much information we want to store. Let's store 4 numbers. Always end your line with a semicolon, of course. How do we assign these values now that we've created an array? Well, to do that, we can use our square brackets again. So remembering from our example before that we count from 0, we can assign the first element in the array by using index 0. And then we can just set that equal to whatever number you want. Let's use 3.14 for example. Now, in this example, we are attempting to assign, and look, we've got an error here. It says that my number is undefined. Now, in this example, if I make sure to put S here because I called this array my numbers, make sure your names match. Now, in this example, in the first position of my numbers, we are storing the value 3.14. If we come up to the top and we include some ability to print, so say using standard output or standard input output rather as a header file, then we should be able to just come down, do our printf statement, and then make sure to use our format specifiers. In this case, we're trying to print a double, which is LF. If you're ever unsure, just search for C format specifiers, and we'll just follow that with a new line. And now we just need to give it the value to substitute in place of this %LF, okay? And in this case, we want to just print out that first value in the array. So to get access to the first value in the array, we just can do the same thing again. We just say my numbers, position 0. And this works more or less like a normal variable would. We can assign a variable and we can get the variable back. It's just worth noting that this actually contains a lot of different values and we're just asking for a specific one. So by bringing up our terminal, which you can use Control or Command and the tilde button, which is the button above your tab key on your keyboard, or by going Terminal, New Terminal, you'll be able to bring up your integrated terminal here. Now we can compile our program using GCC array.c, remembering that that's what we called our file. If you called yours something different, you need to make sure you give it the correct file name. And then we will specify the output as array.exe. Okay, so remembering that this is just setting the output name of the program. If you're on Windows, you should follow up with a .exe. If you're on Linux or Mac, you don't have to finish with .exe. This is just a Windows specific thing. Okay, running our program, you see it compiles correctly with no errors, and we've actually created an array.exe file, which is a binary program that we can't actually look at in VS Code. So we know it compiled well. To run our program, on Windows, we simply have to say the name of the command, which our program is called array. But if you're using Mac or Linux, always remember to do a / and then the name of the program you're trying to run. It's a little bit of an annoying difference, but it does exist. Okay, so running our program as array, let's see what happens. And perfect. You can see it worked. So when we tried to print the first value in the myNumbers array, it correctly printed 3.14, which is the number that we stored in this array. Now, if you're wondering why there's extra zeros here, it's because a double is always just going to have zeros after it, but even if we don't define them, but that doesn't change the value of it at all. So that's kind of what we expect. What happens though if we try and print a number that we haven't directly assigned to? Well, let's print the second element. Remember that we start counting from 0, so 1 is the second element. Let's try printing the second element in the array, knowing that we haven't actually set a second value anywhere. Compiling our program again and running it, you'll note that it's been nicely zeroed out. And this is more or less some behavior that you can maybe expect to happen, but don't count on happening. In general, I would expect that an array would be initialized to be all zeros before you've assigned it any values, but it is possible on certain operating systems or with certain compilers that you could get absolute nonsense values because we haven't actually set them to anything. So if you want every value in an array to be 0, by default at first, it's always best practice to set that manually yourself. Okay, so, and we can go ahead and we can set this now to something different. So say my number in the first index, okay? And let's assign that to, I don't know, maybe 6.5, for example. Okay, so now I've made an additional tweak as well as assigning the first element here. And there is a bug here. I want to see if you guys can spot it. And if you've thought that it might be this 5, you'd be correct. Because remember, our array only has 4 elements. So counting from 0, that means we can only actually assign 1 to 3 as values. If we say copy this a few times, 2 and 3, right? Those are all of the values we're actually allowed to assign. Okay, we can't actually assign any more values than that because remember, we've said the array contains 4 numbers. And so here, starting counting from 0, we get 0, 1, 2, and 3. And this is 4 separate values. So this is the maximum number. So assigning something to position 5 is well out of the bounds of the array. Like well beyond the index of what we've said we were going to store in there. And if we do this and we try and compile our program, oops, that's not the right key for it. Let's compile our program and then running it, we'll now get an error. Now this will look very different on very different operating systems. Sometimes you'll see something called a seg fault. Sometimes you'll see an access violation. Sometimes you'll just get a cryptic error message with no obvious understanding. Generally, when you get really confusing errors like this with no explanation or a segment fault error or an access violation error, it means that you have tried to write information to an area of memory you don't have access to. Now, remember that when we create an array, we store the pointer to the first value on the shelf. Well, what happens if we add 5 to a pointer that is only supposed to have 4 elements? Well, now we are pointing to a part of memory that we were never expecting to be addressing. And that results in a pretty big problem. It means that we're writing to random parts of memory which we didn't intend to write to, and that could mutate program state and cause a bunch of errors. So it's always important to remember that you should only write the amount of values that you originally declared. Now, sometimes it is possible to overwrite an array. For example, if I do my numbers and 4 and set this equal to some value and printing it out, you might expect that this should also cause an error. And in some cases, this would error immediately. But on some operating systems and compilers, it might let you, in some cases, overwrite the end of the array. Remember, we're only supposed to have 4 values, and these here is already 4 values. So by assigning to this position, you should in theory be out of range of our array. But we can try compiling this program and see if it'll let us do it. And indeed, it did without any complaints. As you can see, it correctly assigned and printed it out. And that can work. It mainly means that you got lucky. It basically meant that the next piece of memory that you tried to access was free, and so it just let you write to that piece of memory, even though you didn't originally ask for that to be allocated. But this is risky business, and it can cause bugs which cause your program to suddenly stop working when the last time you compiled it, it did work. Sometimes it can even cause programs to run and then not run on the same compilation. So it's important to understand that we don't create bugs like these because they can be really hard to debug as a beginner. So always remember that we count from zeros in our arrays. And by counting from 0, that means that our last number is always going to be 1 less than the length of the array. So this is a really basic look at arrays, and arrays become really powerful when you pair them with loops. And loops is something that we will look at in the next episode. We'll go into a bit of detail about how loops work, and we'll also show some examples of how loops are useful to use along with arrays. But for now, hopefully that all made sense, and yeah, I'll see you in the next one.